Hello everyone and welcome to this lecture. In the last lecture, we have started the discussion on algebraic connectivity and Feidler vector. What was the algebraic connectivity? It is the second smallest eigenvalue of the Laplacian matrix, and the corresponding eigenvector rather is known as Feidler vector. We have seen that just by looking at the entries of Feidler vector, if we pick suppose all the non-negative entries, the corresponding vertices forms and induce the corresponding vertices. If you talk about the induced subgraph on this, it is a connected graph. Similarly, if you talk about non-positive entries and talk about the vertices associated with this, the induced subgraph on these vertices will again be connected. Okay, today we will start some bounds on the algebraic connectivity, which tells how well connected a graph is. Okay, so let us start with some bound. Okay, so yeah, so let us start with this. Okay, so in order to give the first bound, okay, so maybe I will take maybe one or two lectures for telling about few bounds on algebraic connectivity. So today I think we will be doing with just one bound. Okay, and in order to write down this bound, I need one notation. This notation is with respect to distance between two vertex sets, two subsets of vertex set. Okay, so notation first of all. Okay, notation. Okay, suppose we have two two disjoint vertex subsets. So suppose v1, which is again subset of this. Similarly v2, which again, so for clarity let me write this here. Okay, then the distance between v1 and v2 is actually the minimum of the distance. So this is actually this. I will tell you what distance. The minimum distance between I and j, where actually I is in v1 and comma j is in v2. Okay, and remember dij is nothing but dij is the distance between between I and j. Okay, I and j. And what do we mean by distance? Distance is which is equal to the length of a minimum of a shortest path, I would say, as the length of a shortest path. Okay, between I and j. Okay, so I mean shortest path is what which have again, I mean the shortest means in terms of the number of edges which we are using to reach from I to j. Okay, so the length is the number of edges which are in that particular path. Okay, so yeah, so dij dv1 v2, it is now clear. It's a minimum over all these quantities. Okay, very good. Now we are ready with the first bound on the algebraic connectivity. Okay, so let me now write the theorem. Theorem. Okay, so let G be a connected graph. Okay, connected graph. By the way, for this definition, actually you can also take here G to be connected. Okay, so here G to be connected. Okay, so G is connected. Very good. Okay, so now let us see. Let G be a connected graph. Then first of all, let me write then the algebraic connectivity mu is always less or equal to 1 divided by the distance between v1 and v2 square. Okay, v2 square, and then this quantity. Okay, so 1 divided by v1 plus 1 divided by v2. Okay, and multiply by the number of edges, actually this number of edges in a total number of edges minus total number of edges in, I will tell you what g1 g2 are. Okay, and g2. Okay, so let me write first of all what g1 g2. So mu is clear, distance we have already defined, distance between v1 and 2. So g1 is the induced subgraph on v1. Okay, induced subgraph on, remember v1 was again a subset of vertex set of G. Okay, then similarly g2 is actually the here, so the g2 is the induced is the induced subgraph, okay, on V2. Again we subset, and V1 and V2 are disjoint. Okay, so V1 comma V2 are disjoint. Okay, so how to prove this? Okay, so this statement is slightly lengthy, but there are many beautiful corollaries of this, beautiful consequences of it. This we will see in the next lecture, but let us prove this nice theorem in this lecture. Okay, but how to prove it? What can be a good hint for us? Okay, so it consists of the distance between V1 and V2, and then of course the edges are playing role, and the size of vertex it is also playing role. Okay, very good. So let us start with this. Okay, so let me cook one quantity for each vertex. Okay, so proof is this: for all I, okay, suppose gi is this quantity. So gi is 1 divided by the number of vertices in V1. Okay, and then maybe this distance. Okay, so distance between V1 and V2. Okay, times this 1 V1. Okay, very soon you will get some intuition why I am writing this. Okay, and then plus 1 this, and then you multiply this quantity. By the way, this quantity is yeah, here it is not a problem, but here you have to be very careful that this quantity times the minimum of the distance between I and V1. Okay, and the distance between V1 and V2. Okay, so this quantity. Okay, so if you see that, just focus on this. So suppose if I belongs to V1, then what will be this quantity? In that case, this quantity will be what? So I is V1, then V1 is actually 0, so this whole quantity will become 0. Then gi is nothing but 1 divided by V1. Okay, and what if I is belongs to V2? Okay, then gi is what? Okay, if I belongs to V2, then what? These two quantities are same, but this then the distance will be nothing but distance of V1 V2, which will be actually cancel out with this distance of V1 V2, so it will be divided by this, so it will be 1, and then 1 divided by mod V1 minus this quantity, so it will come out to be minus mod V2. Very good till here everything is fine. Okay, now the next thing is, now suppose I and j have an edge. Okay, so suppose if I and j have an edge between them, in that case if you see that this quantity the distance between I and V1, okay, minus the distance between j and V1, if you take mod of this will always be coming to less or equal to 1, right? Because there is just one edge, you're just one step away from each other eye. Okay, very good. Now this implies that if you subtract gi minus gj in that case, then in that case gi minus gj, this quantity will be always less or equal to from here if you see, this quantity will be always less or equal to this number, right? So this mod will be always less or equal to d of v1 comma v2, okay, and then this number, right? v1 plus this v2. Very good. Okay, very simple stuff up to now. Okay, so now what next? Let me think what next we can do. Okay, so this we have done this. Yeah, very good. So correct. Now let us define a new quantity. Okay, this new quantity is actually average of all g. Okay, all gi's. So let's suppose this gi is nothing g bar, you can say, is nothing but summation over all gi's. Okay, summation over all gi's and divided by n. So this is kind of average. Okay, then we will try to cook one vector whose ith entry is this, whose ith entry is fi. Okay, so suppose fi is equal to gi minus mod g, okay, sorry, g bar, average of g for every I, and f is your this vector, f is your suppose this vector f1, f2, okay, and dot fn. There are n number of vertices. Okay, now let us focus on the this quantity f transpose LF. Remember, now you actually recall what I am going to do. Okay, we will make use of that Rayleigh quotient or the optimization version of the second largest eigenvalue, second smallest eigenvalue here, because we are dealing with Laplacian matrix. So this is nothing but, if you take summation over all I and j, okay, so this is nothing but fi minus fj, fj, and this square. Okay, so this we have seen multiple times. And by the way, due to this definition, this quantity is nothing but this, right? This is nothing but summation over all I and j, okay, gi minus gj, right? Gj and then whole square. Okay, now remember, if I belongs to, if I or j both are basically this, if I and j both are in V1, or if both are in V2, okay, then we have seen that this is nothing but then the gi, actually gi equal to then gi is equal to gj, and in this case this quantity will be 0. Okay, this quantity will be 0. Okay, then we have to deal with when I and j is, so let us consider the case. Let us consider the case when basically this ij belongs to, I mean, it is not in our case when I is not in either G1 or G2. Okay, so this is other edge. Okay, so in that case, if you do this, so this is nothing but so let me write this F transpose Lx again. So F transpose F is equal to summation over all ij's. Okay, and then this was gi minus gj. Okay, and you are taking the square of this. Okay, you are taking, okay, so now if you see that what will be this difference, we have already seen one inequality for this. If you see, when there are edge, right, between I and j, I mean, this inequality holds. So basically this is equal to, now let me write it, this is equal to, so for any I and j, so the gi in this case, let me write, in this case, okay, gi minus gj, okay, mod is always less or equal to, okay, so let me again say it. So what was that inequality? This inequality was 1 divided by distance and then the terms of inverse of mod. Okay, so 1 divided by the distance between v1 and v2, and then quantity 1 mod v1 divided by, okay. Now how many such edges are there? The number of these edges is nothing but the number of such edges is what? So remember, these are the edges which are not in either of G1 or G2. So this is nothing but as EG minus G1 minus EG2. Very good. Is this. Okay. So maybe now we can. So I think I have to make mod here in the expression. If I have forgot. Maybe I have not for. So this has to be mod. Okay. This has to be mod number of edges. Okay, very good. Sorry about that. Okay, great. So now what next? What next we can do? Okay, so this means that F transpose LF, okay, is equal to, in fact less or equal to, now will be less or equal to this quantity times, so 1 divided by dv1 v2. Okay, and we have to actually take a square of all this, right? So this 1 v1 plus 1 v2, okay, and you take a square of this quantity times this quantity times, let me write in slightly into, let me write it here, mod eg1 eg minus eg1 minus eg2. Okay, and yes, very good. So let me put this vector. Very good. Now this is now I said you might, as soon as I write this, you might get hint that what I am going to do next. Okay, so in order to use railway quotient, so let us calculate what F transpose F will look like. Okay, F transpose L, F transpose F. Okay, by the way, this F is orthogonal to all one vector. Why it is so? You just see by looking at the definition of F, right? Definition of F, I have given it here. Okay, so this is nothing. If you add all these entries, it will give you 0 because we are subtracting each entry with its average. Okay, so this is orthogonal. Okay, now we are at right direction. Now let us see what F transpose F will be. Okay, so this is nothing but summation over all I and then Fi square. Okay, now let us take only the vortices which are in V1 and V2. So this quantity is always greater than so all the i's basically summation over all the i's which are in either V1 or V2. Okay, which are V and then Fi square. Very good. Okay, so this is equal to, further if you calculate, Fi is when I belongs to V1, we know what Fi is, right? In that case, this is nothing but 1 divided by V1. Okay, and then you subtract the basically what are the average of this, right? So average of G. Okay, and then in case of, and how many times this is coming? This is coming time mod V1 time, right? Okay, and then you do square of this. Very good. Similarly, this will be what if I belongs to V2. In that case, this will be the GI quantity will be what? GI quantity will be nothing but, I think, minus 1 divided by V2, but and then you are subtracting minus G2, but you are taking square, so this will be nothing but mod V2 times 1 divided by V2 plus G bar square. Okay, now if you open this quantity just by squaring, right, you will see that this quantity is again this follow that this is nothing but 1 V1 plus 1 mod V2. Okay, very simple step. Just open it by doing squaring. Okay, and this will be equal to this. Okay, what next? The next thing is very simple. We know that mu is always less or equal to F transpose L F again. Okay, so let me erase it. Okay, LF divided by F transpose F by just Rayleigh quotient. Okay, and then these things are immediate, so this is nothing but this we can actually put, so this is equal to, in fact less or equal to, I would say, we have seen this quantity, right? So F transpose LF is what? F transpose LF is, yes, this quantity. So yeah, so let me actually write down this. Yeah, so 1 divided by mod V1 plus actually I'm forgetting again, so let me, it was distance square and then this. Okay, very good, so it was distance actually. Okay, so the distance of V1 comma V2 square. Okay, and then the quantity here, if we write this, right, then the quantity 1 divided by mod V1 plus 1 divided by mod V2. Okay, and then again square. Okay, square of this quantity, and then actually we are multiplying with the number of edges which are contributing to that term. So times E of G minus E of G1 minus of E G2. Okay, and then you divided by what? This, right? So F transpose F, because this was greater, so this inequality will fall because it's in new denominator term. So 1 divided by mod V1 plus 1 divided by mod V2. Okay, so you can actually cancel this by this. So now the result is immediate from here. So you can now write this as mu is less or equal to 1 divided by the distance between V1 and V2 square. Okay, times this, right, mod V1 plus there is no need of actually mod here. Okay, so and then times what? Then times this number of edges here minus number of G1 minus number of G2. Okay, very good, and we have proven this. Slightly lengthier statement, okay, but we will see many good applications of it or direct consequences of this fact, okay. So yeah, so I'm stopping this lecture here and see you in the next lecture. Let me actually, before moving for the next lecture, let me actually check whether I have actually written the statement of the theorem correctly or not. So let me go back. So yeah, so it was written correctly. Now we will see many good immediate consequences of this slightly lengthier looking inequality, and for this let us wait for the next lecture. Thank you very much and see you in the next lecture.